At the heart of our galaxy lies a cosmic monster, a supermassive black hole known as Sagittarius A. Silent, invisible, yet powerful enough to shape the Milky Way itself. Tonight, we'll explore its hidden depths and quiet fury. If you enjoy this journey, please like, subscribe and share, and tell us in the comments, do you think black holes create or destroy more than we know? Thank you for watching. Now, let's begin. From a great distance, the Milky Way appears as a pale disk of starlight with two strong spiral arms, a fainter pair that lace outward, and a central bar of older stars set on a gentle slant. The disk is thin compared with its span, and dusted with dark lanes that veil portions of the light. Where the bar meets the arm's star formation kindles in knots and ribbons, while the outskirts fade into a quiet halo of ancient widely spaced suns. Across this sweep, gas and dust drift in cold streams, warmed here and there by clusters that carve bubbles in the interstellar medium. All of this motion points inward with a patient rhythm. The bar slowly turns shepherding material along curved shocks that ride the inner arms. The arms themselves guide clouds on long paths that only gradually tighten. The halo encloses the system in an unseen mass that steadies the overall spin. At the very centre, the bulge rises like a rounded city of stars densely packed and old mixed with younger pockets kindled by the compression of passing waves. In that crowded light, the lines between individual suns begin to blur, and the glow thickens into something almost solid. Dust streaks the bulge in broad lanes that eat starlight and re-radiate it in longer wavelengths. Seen from above, the bar and bulge act together as a funnel drawing gas inward along lanes that arc like river mouths toward a bay. Seen from the side, the disk becomes a narrow blade with a central swell and a dark seam cutting across it, a reminder that much of the central story hides behind curtains of dust. The nearer the gaze moves to the heart, the more the sky changes character. In the outer disk, blue clusters and wide dust clouds pick out the spiral design, and the spaces between them are broad and quiet. In the inner regions, the interstellar medium grows busy and tangled, cold molecular gas pools in dense clumps, warmer streams slide past in shearing layers, hot plasma bubbles drift above and below the plane. Magnetic fields thread the region, and sometimes show themselves as long, narrow structures that cross the grain of the background light. Supernova remnants punch cavities that later fill with fresh gas. Stellar winds from massive clusters drive fountains that rise and fall like slow tides. The outcome is a network of rings and streams that circle within a few hundred light years of the centre, a zone where gravity, pressure and turbulence all claim authority. This central molecular zone is not a uniform ring, but a broken belt with gaps, spurs and arcs that carry gas on elongated orbits. Tidal forces are strong enough here to shear clouds into filaments and to stretch them along their paths. As clouds round the inner turn, shocks and collisions trigger brief flashes of star formation, then pressure and radiation peel away what those young stars no longer hold. The result is a dynamic landscape in which stars are born, move on, and leave behind cavities that later close only to open again elsewhere. Deeper still, within a few tens of light years, the stellar crowding becomes severe. The nuclear star cluster occupies this space, a compact aggregation where the average distance between suns shrinks dramatically compared with the calm surroundings of the solar neighbourhood. Orbits tighten, relative speeds rise, and gravitational encounters heat the cluster in a slow dance that rarely leaves any star entirely alone. If an observer could stand within this region, the sky would never grow dark. It would be lit by a permanent twilight of countless suns, their light reddened by dust but intense all the same. The The starlight that reaches telescopes from this zone is sifted through heavy extinction, yet infrared views recover an astonishing number of sources enough to map the gradients of density and to outline the motion of the population as a whole. The bulge itself is not a statue. Resonances in the bar capture stars into shared families of orbits, sculpting a subtle, boxy or peanut shape when seen from the side. Some stars carry the chemistry of earlier bursts enriched in heavier elements that betray cycles of formation and death. Others belong to younger episodes, perhaps fed by gas recently shepherded inward by a mild change in the strength of the bar or by the wake of a minor merger long since absorbed. Clusters wander through, some dissolving under tides, some surviving to age in place. The bulge is a memory store, but an active one rewritten by each new inflow and each fresh generation of stars. All of this structure serves a traffic pattern. Spiral arms feed the bar steers gas into inner lanes. The lanes fall toward the molecular ring, and the ring and its streams guide material around the last stable turns before the central light thickens into a single glare. Each step inward narrows the options for stable motion. Choices that were easy in the outer disk become costly here, because shocks and tides exact a toll in energy and angular momentum. Dust that reddens starlight also acts as a coolant that lets gas contract, making new stars and altering the balance again. Hot plasma and cold molecular gas occupy the same broad volume, touching along thin layers, where temperature and density change abruptly, and where radiation can leak. The picture is not chaotic for its own sake. There is an order inside the apparent disorder, a global circulation that moves matter inward, on paths that look tangled at small scales, but add up to a slow inward transfer at large scales. The innermost light years hint at an even deeper organizing force. Even when the core shines, faintly nearby stars move as though a heavy hand rests at the very center. Their random directions add up to a pattern imposed by a compact mass that is small compared with the cluster, and yet rules its immediate neighborhood completely. At this distance, the presence at the center cannot be seen directly. It declares itself through the paths of stars that pass close, and through the shape of the gas flows that skirt an invisible boundary. The bulge supplies the stage, the cluster provides the crowd, the molecular streams bring the props, and the bar cues the entrances. In that layered theatre, the heart of the galaxy sits quiet, patient, and decisive. The story of the outer structure matters because it sets the conditions that any central engine must satisfy. If the core were too violent, the bulge would not retain its measured form. If the feeding were too rich, the inner lanes would flash with sustained brilliance rather than brief episodes. What is seen instead is a system that appears balanced in a long, slow exchange, an inward drift of gas, and a steady shaping of stars, all converging toward a point that does not shine by itself like a star, yet governs the motion around it. The distance view ends here on the last ring, where the city of stars stands crowded, and the lanes of dust arc inward. Beyond this line, the light grows redder, the stars move faster, and the motions begin to mark out a compact region that will soon dominate the narrative. The Milky Way has led the eye toward its core with a soft hand, and the core has answered not with spectacle but with gravity. The next step will not be a leap, only a narrowing, as the gaze moves from the scaffolding to the engine that the scaffolding surrounds. Long before sharp infrared images reveal crowding near the core, the first persistent sign of a compact presence arrives as a murmur in radio waves. The line of sight toward the center runs through thick lanes of dust that swallow visible light, but long wavelengths slide through with much less hindrance, carrying news from the hidden heart. In the middle decades of the 20th century, large dishes and simple arrays begin to map the inner sky, and observers notice that the region around the constellation of the Archer holds a complex glow stitched with bright knots and winding filaments. This diffuse quilt of emission is not a single object, but a population of sources, some extended, some sharp, all layered along a busy line of sight. It takes patience and better angular resolution to separate the voices in the crowd. As instruments grow, baseline lengths stretch receivers quiet, and data handling improves. Astronomers begin to pick out a small, steady beacon tucked into the confusion. It does not dominate by brightness, it stands out by persistence. Night after night, season after season, it remains fixed at the dynamical center, as though nailed to an unseen pivot. The name that settles upon it is simple and precise, a tag that says only where it lives, the Archer's center, Sagittarius A. Within that label, a more compact brighter point earns a star symbol to mark its special status. The star is not a star at all, but the notation hints at how it condenses attention. The path to confidence is slow, because radio waves pay a toll as they cross the central environment. Irregularities in the ionized gas act like a shifting glass, scattering the signal into a blurred disk that grows with wavelength. At the longest wavelengths, the beacon seems swollen as if it were physically large. At shorter wavelengths, the scattering curtain thins, the image tightens, and the source shrinks, revealing that the apparent size is mostly an effect of a rough medium, rather than the true form of the transmitter. This behavior already suggests a compact origin, because only a tiny engine can keep its identity after so much smearing, flaring, and interference. Arrays working at centimeter and millimeter bands measure a spectrum that rises and falls in a way that implies self-absorption close to the core and a transition to optically thin emission at higher frequencies. The emission mechanism points to charged particles spiraling in magnetic fields, shedding energy in a broad smear of radio light. None of this by itself proves the presence of a black hole. It does, however, peel back the first layer of disguise. The bright knots nearby turn out to be supernova remnants, star-forming regions, and thermal filaments that lace the inner few hundred light-years, but the compact point refuses to share their properties. It is non-thermal in character, compact beyond the reach of early beams, and anchored at a position that matches the dynamical weight of the entire bulge. The geometry argues that this is the true center, not just a bright neighbor. As radio maps improve, a distinctive feature unfolds to the north of the core, a narrow structure that runs nearly straight for many light years. Other filaments join the scene, each tracing magnetic order, where the gas is otherwise unruly. These threads are not direct evidence for a central mass, yet they frame the stage with clues about how energy flows through the inner environment. The compact source sits at the crossing of these hints, a quiet node in a tense fabric. Variability enters the story early. Though the source is steady on long-time scales, it flickers on shorter ones with flux rising and falling over hours or days. This behavior matters because a changing light curve implies a limit on the size of the emitter. A region cannot brighten or dim faster than it can coordinate its own signal across its span. Therefore, the timescale of variation places an upper bound on the physical dimensions of the source. Radio watchers build a case that the core is not only compact in the plane of the sky, but also compact in time, a pulsing ember rather than a wide hearth. Curiosity pushes to higher frequencies where scattering grows weaker and angular resolution improves. Observatories in dry high places attempt millimeter and sub-millimeter work, chasing the true silhouette of the central engine. At these frequencies, the spectrum bends again, and subtle changes in polarization appear, small rotations in the preferred direction of the electric field that hint at ordered magnetism near the source. Polarization can twist as waves pass through magnetized plasma, a process that writes the structure of the intervening medium onto the radio light. That twist measured across frequencies becomes a yardstick of the magnetic environment and the density of the charged gas. Each new measurement suggests that the heart sits inside a magnetized turbulent bath where fields are strong enough to shape the flow of hot plasma. Tied to these developments, timing campaigns coordinate with high-energy observatories in orbit. When an X-ray flare erupts near the core, radio telescopes watch to see whether a corresponding change ripples through the longer wavelengths. Sometimes a delayed brightening follows, as though a small explosion near the center has pushed energy outward along the flow and into a region that shines more readily in radio light. At other times, the connection is less clear, leaving room for multiple paths by which energy moves from the inner zone to the surrounding medium. The absence of a clean pattern does not weaken the case for a compact engine. Instead, it shows that the innermost environment is a web of processes with different characteristic timescales and preferred wavelengths. Interferometry adds a decisive tool. By linking distant dishes across continents, very long baseline techniques synthesize a telescope with a diameter measured in thousands of kilometers. The scattered image narrows, the compact source sharpens, and its position solidifies with exquisite precision relative to nearby star clusters and maser beacons. The signal still blurs at the longest wavelengths, because the interstellar medium continues to ruffle it, but the underlying size remains so small that the scattered spot would collapse to an even tinier point if the curtain could be fully lifted. Here, radio astronomy accomplishes a paradoxical feat. It shows something by showing how little can be shown. The inability to resolve the core at modest baselines is not a failure. It is a measurement of compactness. In parallel, gas kinematics near the center provide a complementary radio anchor. Spectral lines from molecules orbiting within the central molecular zone show high velocities and strong gradients, a signature of intense gravity at small radii. The pattern of these lines sketches the pathways by which gas flows inward stalls or swings past the core in elongated loops. The compact source sits at the meeting point of these streams, sometimes quiet, sometimes restless, as though the flow laps at a shoreline that retreats just out of reach. The picture that forms from these radio whispers is both modest and profound. The core is dim compared with the famous mighty engines in distant galaxies, yet it behaves like a central engine scaled to a calmer diet. It glows with non-thermal light. It hides behind a scattering screen that thins with rising frequency. It flickers on timescales that argue for a small physical size, and it lives at the unique balance point of the bulge, where every stellar orbit would precess around it if given enough time. Each fact is a small stone. Together they build a foundation strong enough to bear more daring tests. The intrigue deepens because the radio source does not act like a star cluster, a supernova remnant, or any ordinary cloud. It is too compact, too persistent, and too central. To explain all of these traits without a black hole demands contortions that grow more strained with each new observation. The radio path does not shout its conclusion. It hums it over and over until the tune becomes hard to ignore. Still, one essential step remains. A compact radio beacon at the exact center is compelling, but gravity writes its clearest signature in motion, and stars near the core carry that script in their orbits. The radio story has shown where to look and what to expect. Now the task is to watch the fastest stars and to see whether their paths draw a boundary around a mass so concentrated that no cluster of dark remnants could mimic it. The radio whispers have led the way. The coming infrared vision will lay down the tracks that circle the unseen engine with measurable grace. The fastest stars near the heart of the galaxy become test particles in a natural experiment that no laboratory can build. They move through a crowded field, yet their paths carry a clean message because gravity is simple at the center, a single pull that dominates every rival. For a long time, these stars hide behind dust, their light swallowed before it reaches ordinary telescopes. Then infrared work reaches the sharpness needed to separate one shimmering point from another, and techniques tame the blur of Earth's atmosphere. Speckle imaging breaks long exposures into many brief snapshots and recombines them to recover detail. Adaptive optics watches a reference point in real time and reshapes a mirror to cancel distortions carving through the trembling air and sliding open a window on the true scene. With those tools, large telescopes on high dry summits turn toward the core and hold their gaze for year after year. They mark the positions of thousands of stars, and within that crowd choose a few dozen whose motions are the most dramatic. These chosen ones sweep close to the very center, then swing far out again, completing loops that fit into human timescales. Astronomers assign simple labels to track them, but the simplicity of the labels does not blunt the astonishment of the orbits. The paths are not random scribbles. They are neat ellipses tilted in three-dimensional space, each one obeying the same invisible focus. When the points are connected over many seasons, an outline emerges that leaves no room for an extended dark object. The mass must be concentrated within a region smaller than the smallest loop, and that region is tiny on the scale of the cluster. One star in particular becomes a clock for the center. It completes a full circuit in a span of about 16 years, a period short enough that one research generation can watch it pass through closest approach twice. Near that point of closest approach, the star dives inward until it is only a small fraction of a light day from the focus. Its speed rises to several thousand kilometers per second. This is not a guess, but a measurement. Positions change from month to month by amounts that precise cameras can track, and spectral lines shift in wavelength as the star races along its path. The combination of proper motion on the sky and the radial pull along the line of sight gives a three-dimensional track, a complete story rather than a shadow. The story's conclusion is firm. Within a region smaller than the orbit of a planet there sits a mass of several million times the mass of the Sun. No cluster of dark stars or remnants can be packed so tightly and still remain stable for the lifetime of the galaxy. The only known way to hide that much weight in that smaller space is a black hole. The label does not end the curiosity, it sharpens it. The orbits allow more than a mass estimate. They probe the shape of the gravitational field and the motion of the mass itself. If the center were smeared out even a little, the ellipses would not close neatly. Small tugs would warp the paths in ways that a careful analysis could spot. Instead, the ellipses return upon themselves with a precision that argues for a point-like source, at least on the scales that the current baselines can test. At the same time, there are hints of gentle precessions, small rotations of the orbits that may encode the influence of the broader nuclear cluster, the distribution of dark remnants, or the deeper predictions of gravity in its strong form. The work demands patience and humility. Each measurement must be tied to a stable reference frame, and the reference frame itself must be checked against distant beacons so that a drift does not masquerade as a physical effect. Even the apparent stillness of the core must be tested. If the central mass wandered by even a small amount under the push and pull of nearby stars, that motion would smear the focus. Yet repeated observations align the focus with the compact radio source called Sagittarius A star to within astonishingly small errors. The radio and infrared centers coincide. Gravity and emission point to the same spot. During the most dramatic passages, the infrared light of the clock star carries additional marks. As it sweeps through pericenter, its light is stretched by gravity and by its own speed. The detected spectral lines shift in a way that agrees with the predictions of general relativity for a test particle, moving through a deep potential well. The star dims and brightens in step with its quickening and slowing. Timing and spectra together become a cross-check telling a coherent tale about the shape and depth of the well. Each successful prediction builds trust in the mass and compactness inferred from the geometry of the orbit. The surrounding cast of stars adds texture to the stage. Many of them are surprisingly young for such a hostile neighborhood, with masses and temperatures that suggest recent formation. Their presence raises questions about how starbirth proceeds in a tide field that should shear fragile clouds apart. Perhaps disks of gas once orbited the center and fragmented under their own self-gravity. Perhaps clusters born farther out migrated inward and were shredded, leaving streams of young stars behind. In either case, the result is a population that tests the central pull across a range of distances and orientations. Some orbits are nearly circular, some are elongated, and a few are wild, plunging deeply inward before swinging back out with long, slow arcs. Taken together, they outline an almost spherical concentration of mass with only small departures, as though the black hole sits inside a nest of stars that have not had time to relax into a single family of orbits. The star orbits do more than weigh the center. They help to place boundaries on any hypothetical alternatives to a black hole. Objects made of exotic physics have been proposed for decades, but those objects often predict a surface or a volume where matter could accumulate and shine. The close passages of the fastest star do not trigger persistent surface emission. The center remains dark aside from the variable glow of hot plasma in the accretion flow. If there is a surface, it hides its presence with extraordinary efficiency. If there is no surface, then the horizon idea holds space folds in such a way that paths point inward and do not return. The orbits lead the mind to that threshold, and then stop because stars cannot cross it intact. They can only report the gravity from outside. Even the smallest deviations become tools. Tiny changes in orbital timing might betray clusters of unseen stellar remnants, or the slow drift of the central mass as it trades momentum with its environment. Small alignments among orbital planes could hint at a past disk that guided formation. A faint spin of the central mass might eventually twist nearby paths in a way that careful monitoring could detect, offering a direct sense of how fast Sagittarius A star turns. Each of these possibilities depends on the continuation of patient watching. Instruments continue to improve. Better correction of the atmosphere, larger primary mirrors, and more stable spectrographs all push the frontier inward. New interferometric methods at infrared wavelengths begin to tie light from many telescopes into a single sharp beam, increasing resolution to scales comparable to the orbits themselves. As precision grows, the possibilities for confusion also grow because the core is busy. Flares brighten and fade. Hotspots may trace brief loops near the horizon. Gas streams slide across sightlines, adding and subtracting extinction. The art of the work is to sift these disturbances from the steady pull of the central mass. Yet through all of this weather, the main result stands like a lighthouse on a rock. The orbits remain closed, the mass remains concentrated, and the focus remains on a single compact point that coincides with the radio source. The stars have written the script of an invisible giant, and the script does not easily bend to any story other than a black hole. The mystery deepens because these clear answers open new questions. How does so massive an object feed so feebly most of the time and yet flash with sudden energy? How are young stars born in a field of tides that should tear their cradles apart? What influence does the black hole exert on the life of the inner bulge over very long times? The orbits offer the mass and the map, but they also outline the edge of understanding. Beyond that edge, the glow of hot gas and the snap of magnetic fields begin to govern what can be seen. The next turn will leave the clean geometry of stars and step into the fluid realm of plasma, where light flickers, fields twist, and time itself becomes a measuring stick for structures too small to resolve. Weighing the central engine begins with geometry, timing, and patience. The inner cluster draws a map in motion, and the map translates clean positions into a clear mass. When an orbit completes its loop, the period and the size together yield a measure of the gravitational pull at the focus. The fastest stars offer the tightest constraints because their paths pass nearest the centre and return within spans short enough for people to witness. Their ellipses close around a point that does not shine like a star. The enclosed mass derived from these paths reaches several million times the mass of the Sun, and that total must live inside a space smaller than the smallest orbit's closest approach. This pairing of large mass and tiny volume rules out all familiar forms of matter. It also sets the scale for everything that follows the speed of nearby stars, the temperature of the inner plasma, the pressure of the environment, and the timings of flares that rise and fall like sparks in a wind. The size limit sharpens as techniques improve. Infrared interferometry ties together separate telescopes, and the linked baselines slice the glare into finer detail. Positions once good to the width of a human hair at the distance of the moon grow finer still, and any wobble of the central point would reveal itself as a slow drift or a widening of the focus. Yet the focus stays put to within extraordinary limits, aligning with the compact radio source that marks the dynamical center. The measured orbits not only weigh the mass but also confine it. If the central object were a cluster of many dark remnants, those remnants would scatter one another and heat the cluster until it swelled. A tight bundle of many bodies would dissolve on timescales far shorter than the age of the galaxy. The observed stability of the focus coupled with the high speeds of the nearest stars leaves essentially one option: a single compact object with a horizon that hides its interior. Having weighed the center, astronomers turn to clocks closer to the edge. The inner accretion flow brightens in the infrared and in X-rays with bursts that last minutes to hours. The rise and decay times of these flares act as rulers for the smallest scales, because no source can coordinate a rapid change over a region larger than light can cross in the same interval. A flare that doubles and halves in brightness over a handful of minutes must be produced within a zone measured in only a few light minutes across. For a mass of several million suns that size corresponds to a region not many tens of event horizon diameters wide. The behavior of the light, its polarization and its timing hints that blobs or hotspots may briefly orbit just outside the point of no return, tracing loops so fast that space and time bend their paths into tight circles. The very notion of a horizon, a surface that is not a surface, finds indirect support in these numbers. If there were a solid surface in falling gas would strike it and release a steady glow that would build up in time and persist. Instead, the core remains faint most of the time, and its flashes fade without the lingering heat a hard wall would impose. In parallel, the spectrum at millimeter and submillimeter wavelengths lifts one more corner of the veil. As observations climb to higher frequencies, the blurring caused by the turbulent plasma along the line of sight grows weaker, and the apparent size of the compact source shrinks toward an intrinsic value. Very long baseline arrays that span continents begin to resolve structures on scales comparable to the expected shadow of a black hole. The image is not yet a clean ring in every campaign, but the angular size and the brightness temperature agree with models of a hot plasma near a horizon rather than with any extended cloud. Combined with the dynamical mass from stellar orbits, these horizon-scale measurements lock the solution into place. The object at the center has a size set by gravity alone, a mass set by the dance of nearby stars, and a dimness that fits a weakly fed accretion flow. The balance among these traits is not trivial. A more massive object would enlarge the horizon and slow the orbital times near the edge. A lighter object would do the opposite. The observed flare times, when paired with the dynamical mass, point to a consistent picture in which a compact horizon governs a thin diet of gas. Measurements of gravitational redshift during close passages of fast stars provide an additional test. As a star dives inward, its light loses energy, climbing out of the deep central potential, shifting to longer wavelengths in a way predicted by general relativity. That shift is small but measurable when spectra are taken with stable instruments during the brief window around closest approach. The match to theory strengthens the claim that the gravity near the core behaves as a point-like mass would behave, not as a smeared distribution. The weight of Sagittarius A is therefore not a single number, but a network of constraints. Orbits give the enclosed mass. Flare timescales fence in the size of the emitting region. Polarization rotates in a magnetized flow at densities consistent with the same picture. Horizon scale imaging brushes the edge of the shadow that the mass should cast. Each strand could fail alone. Together they hold. The measurement extends beyond the present. Over the lifetime of the galaxy, such a mass alters the fate of stars and gas that stray too near, changing the energy budget of the central parsec. An occasional star might be torn apart, its debris feeding the engine in a brief storm. More often, small asteroids and gas clumps may fall inward and vanish with only a short-lived spark. The cumulative weight of these events is slight compared with the mass already in hand, but they may write themselves into the variability patterns that instruments record. If future campaigns catch a larger feast in real time, the clockwork derived from the current mass will predict how the flow should respond and how long the afterglow should last. The act of measuring a monster clarifies its restraint. Many supermassive black holes in distant galaxies beam with jets that blaze across intergalactic space, yet the center of the Milky Way remains modest. Its mass is large by human standards, but ordinary when compared with the giants of the universe. Its accretion flow is hot but thin. Its environment is turbulent but not catastrophic. The engine waits at the center of the Baroque inner architecture, patient and mostly quiet yet decisive, in setting the stage on which the inner cluster moves. The measurement therefore doubles as a promise. If gravity is this strong at such short scales, then the near-horizon realm will be a theatre, where time delays, lensing and magnetic turbulence all speak with crisp accents. To hear them properly, observers must combine the long view of stellar dynamics with the rapid heartbeat of flares and the fine detail of horizon-scale images. Each advance defines the next question. How fast does the central mass spin, and how is that spin oriented with respect to the orbits of the young stars and the flow of the inner gas? How often does a larger meal arrive, and how does the engine respond when it does? The weighing is complete enough to ground these questions, yet open enough to welcome surprises. The monster at the center is not just heavy. It is finely measured, and the measurement draws the eye closer to the edge where gravity sculpts light and time into new instruments of discovery. Between the bright bulge and the compact heart stretches a layered environment of dust gas and faint glow, a realm where the traffic toward the center organizes itself into streams, arcs and knots that change with time but obey a larger pattern. The first feature that stands out in infrared and radio maps is a broken ring of molecular gas within a few hundred light-years of the core. It is not a perfect ring, but a lopsided belt, thicker in some sectors, thin and torn in others, a structure shaped by the bar's slow turn, and by shocks where inflowing material meets tighter orbits. Clouds within this belt are heavy with molecules that form only in shielded cool regions, yet they are threaded by warmer strands that trace places where turbulence stirs and where passing waves compress the medium. Each cloud is not a single object so much as a loose family of clumps that collide, merge, and shear. Gravity pressure, magnetic fields, and radiation all claim a share of authority here, and no single ruler dominates for long. The ring is a way station. Gas that rides the inner bar lanes does not plunge straight to the center. It loses angular momentum in steps as it negotiates resonances and shocks, then stalls into looping paths, whose closest approach sets the ring's average radius. Where lanes meet the outer edge bow, shocks form and slow the inflow a little more. In those arcs, densities rise, temperatures change, and chemistry responds. Heavy molecules that once hid in cold pockets are released and destroyed, then rebuilt downstream. The result is a patchwork of spectral signatures that chart the flow as clearly as footprints in damp sand. The ring flickers with brief episodes of star formation when a clump grows dense enough to fall in upon itself despite tides. These episodes are short and local, because the wider environment remains hostile to fragile cradles. Winds and radiation from the newborn stars push back the same gas that fed them, carving cavities and arcs that will later close again as other flows sweep through. Outside, the ring dust lanes angle inward along the bar dark seams in shorter wavelengths that glow softly in the infrared. They are not smooth roads, but braided channels with turbulence etched into their cross-sections, and with magnetic fields guiding charged particles along invisible rails. The lanes feed the ring unevenly. Sometimes a strong pulse arrives along one side while the opposite remains quiet. Sometimes both sides deliver in step, and the ring brightens with many collisions at once. The brightness is not a burst of visible light, but an increase in line emission and infrared glow as grains absorb and re-emit energy. Inside the ring, the view changes. Gas turns away from nearly circular paths and enters more eccentric loops that bring it closer to the center before sending it back outward again. These loops are not random. They belong to families of orbits permitted by the gravitational potential, and their shapes depend on the tug of the bar and the crowding of the bulge. Where families intersect, shocks form and knock angular momentum away, moving a small fraction of the flow one step further inward. In this inner region, dust continues to play a double role. As an absorber, it hides bright stars from direct view, and forces observers to use longer wavelengths. As a coolant, it lets gas shed heat, and compress more than it otherwise could, magnifying the effects of a shock, and making it easier for clumps to survive a passage. Dust grains also carry electric charge and respond to magnetic fields, so they help to trace lines of force in polarized light. In some maps, tall filaments seem to stand upright above the plane, long and narrow threads that cross the central zone. These non-thermal filaments look like taut strings set in a turbulent sea. Their straightness suggests strong magnetic order over many light years. They may be signposts of energy moving outward from the core or of sheared flows that align fields along preferred directions. Their presence adds to the sense that the region is not merely chaotic but disciplined by lines that are hard to see except in special light. Closer still, within a few light years of the center, the gas changes character again. Molecular species that cannot survive high temperatures give way to atoms and ions. The medium becomes partly ionized, and the glow shifts to recombination lines, fine structure lines, and thermal Bremsstrahlung from hot electrons. Here the crowding of stars reaches a peak. Winds from massive stars feed the volume with fresh material, while also heating and stirring it. Each star drives a bubble. The bubbles overlap and merge into a froth that rises and falls with slow tides above and below the plane. The overall effect is a mixed-phase fluid with hot, thin plasma sharing space with warmer, denser streams, and with pockets of cooler gas that cling to shadowed eddies. In such a stew, viscosity is not the quiet molecular property familiar from laboratory fluids. It is an emergent effect of tangled field shocks and waves that pass momentum from one parcel to another. The flow does not drift inward like a uniform river. It hops inward in fits, lingering on certain orbits until a collision, a wave or a magnetic stress nudges it closer to the center. The rate of inflow is modest compared with what might be expected from the sheer amount of gas in the ring. Much of the content cycles within the zone heated and cooled, compressed and relaxed without ever committing to the final plunge. These long conversations among phases explain why the central engine is often faint. The fuel exists, but only a thin trickle reaches the last light year. Even so, the inner flows carry signs of tension. Polarization maps reveal ordered fields near the core, and the sense of rotation of the polarization angle across frequency bands tells of magnetized plasma rotating the plane of radio waves as they pass. This rotation becomes a measure of the amount of charge and the strength of the field along the line of sight, and it changes with time, a hint that the inner flow rearranges itself on human timescales. When a flare erupts in infrared or X-rays, some of these measures respond as if knots in the field tightened and then loosened, or as if a brief injection of energy sharpened a gradient and then let it relax. Sometimes features in the gas take on the role of messengers. A dusty cloud may approach on a long-stretched path drawn inward by the central pull and deformed by tides into a stream that lengthens as it falls. Observers watch such visitors as they brighten and fade. If the path threads the right corridor, the cloud grazes the core heats and sheds some of its skin, then swings away thinner than before. If the path crosses a more direct route, the cloud might break apart entirely, feeding the central hot flow with fresh material that later reveals itself in a train of flares. These events are rare and short, but they confirm the idea that the environment is alive with exchanges. The after-effects ripple through the inner zone for months or years, connecting a single passage to changes far from the original path. The nuclear star cluster adds a steady rain of small bodies to this exchange. Comets, asteroids, and fragments that were once bound to individual stars can be stripped by close encounters and set on wandering paths. Their fates are humble on the scale of the whole system, yet when a fragment evaporates in the hot inner wind or skims the accretion flow, it may trigger a minute flare, a tiny spark in a wide hearth. Such sparks add texture to the otherwise quiet light curve, and keep attention on the fine balance between available fuel and actual feeding. Through all of this, the image of a sink that never overflows remains apt. Rivers of gas fall inward along the bar lanes, pools collect in the broken ring streams, slip through eccentric corridors, and winds from hot stars stir the inner few light years, yet the engine at the centre takes only what matches its narrow throat. The excess is diverted by pressure and by fields into fountains and sideways flows that keep the central region from turning into a continuous blaze. This restraint does not make the zone dull. It makes it intricate. It is a place where small differences in timing or alignment can decide whether a clump survives a turn or dissolves, whether a field line tightens or slackens, whether a flare lights the core or the energy passes outward unseen at a given wavelength. The dust gas and glow are not background. They are the workings of a subtle machine that feeds a compact object with a slow hand, keeping the inner galaxy stable, while allowing brief fireworks that remind observers how close the system is to a more dramatic state. The next layer inward, where the flow turns from mixed phases into a hot magnetized plasma, circling near the point of no return, will reveal how this delicate intake becomes heat and light, and how near the edge the rules of motion twist into new forms. The center's restraint becomes clearest in the puzzle of its dimness. For a mass of several million suns, many might expect a roaring engine, a beacon that rivals the bright cores of distant galaxies. Instead, the heart of the Milky Way glows softly most of the time, with brief sharp flares punctuating a low baseline. The fuel is present in the surrounding rings and streams, yet only a thin thread reaches the last orbits, and even that thread releases less light than simple expectations would allow. The answer lies in how a hot magnetized plasma carries energy as it spirals inward, and in how easily that energy eludes the forms of radiation that telescopes can catch. Near the core, the gas is so thin that particles rarely collide. In a dense fluid, frequent encounters share heat quickly, and energy becomes a common property of the whole. In this inner flow, collisions are so scarce that protons and electrons can wander with their own temperatures and their own fates. The heavier ions carry most of the thermal energy, but they radiate poorly. The lighter electrons radiate well, but they do not easily receive enough energy from the ions to shine at full promise. A large share of the heat is therefore locked into the motion of the flow, rather than cast into space as light. The black hole does not reflect that stored energy back outward from a surface. It swallows the energy as it swallows the gas, hiding the heat behind the horizon. This is one path to dimness, a route where the inner flow becomes a carrier of hidden warmth rather than a lamp. A second path runs through the way magnetic fields distribute angular momentum. To fall inward, gas must shed the spin it inherits from its long journey through the bar and ring. In many cores across the universe, magnetic turbulence performs this task with fierce efficiency, tugging the flow into a thin disk that blazes while it slides toward the point of no return. In the Milky Way, the flow is too lean to settle into a bright thin sheet. It puffs into a thick hot structure where magnetic stresses still move angular momentum outward, but in doing so they also fling some material back the way it came. Outflows carry mass energy and angular momentum into the surrounding volume. Each parcel diverted outward reduces the portion that can approach the horizon. The result is not a simple inward river, but a circulatory system in which only a fraction reaches the deep interior while the rest loops upward or sideways. Observers find hints of this traffic in the polarization of radio light and in the shapes of faint arcs that seem to lift away from the plane. A third ingredient is the speed at which the flow can radiate. Electrons spiraling around magnetic field lines shed energy as radio and millimeter light. The same electrons can scatter their own photons or infrared photons to higher energies, producing a small tail that reaches into X-rays. But because the gas is so thin, the electrons do not collide often enough to share their energy broadly, and the photons they emit can fly out without encountering many partners to scatter. The efficiency remains low. When a flare erupts, it likely marks a local increase in the transfer of energy to electrons, a magnetic reconnection event, or the brief appearance of a hotspot where compression and field lines combine to raise the emissivity. The flare fades when the knot cools, or shears apart and the baseline glow resumes its quiet level. Every piece of this picture carries traces in the data. Faraday rotation at millimeter wavelengths shows that radio waves twist as they cross a magnetized plasma. The degree and the direction of the twist vary with time, suggesting that the magnetic structure near the core rearranges itself on timescales of days to months. The range of rotation also limits the density of the innermost flow, because a thicker plasma would twist the light far more strongly. Those limits fit the idea of a thin diet and a hot diluted medium. Infrared flares rise and fall within tens of minutes with substructure that hints at circular motion near the innermost stable orbits. The combination of rapid timing and polarized light suggest compact ordered regions embedded in a broader, more turbulent sea. X-ray flares occur less often and last longer, as though a small fraction of events tap higher energy channels. Between these spikes, the light curve softens into near silence. That silence is itself a measurement of inefficiency. If the gas were dense or the fields were arranged to trap energy near a radiating surface, the core would glow steadily at levels far higher than those recorded. The quiet is the signature of energy carried inward or outward, without much conversion to light along the way. The underluminous engine, therefore, becomes a clean laboratory for the physics of weakly collisional plasmas. In such media, viscosity is not set by the random jostling of particles, but by magnetic tension and pressure. Turbulence forms and decays not because eddies bump into each other in a thick fluid, but because field lines stretch, tangle, and reconnect. Heat moves not only by conduction from particle to particle, but also by waves and instabilities that shuffle energy along preferred directions. These differences matter for the inner Milky Way because they decide how often energy lands on electrons, how quickly it leaves as radiation, and how strongly the flow resist collapse into a thin, bright disk. The geometry around the black hole adds another layer. If the central spin is modest and the inflow is messy, the inner flow may have no single coherent plane. Instead, it may resemble a set of tilted, wobbling sheets that meet tear and reform on short timescales. Warps and misalignments can stir extra turbulence that helps to drive outflows and to prevent the flow from settling into a high-efficiency state. Conversely, if a longer episode of feeding ever provides a steadier stream with shared angular momentum, the inner flow might briefly flatten and brighten, raising the efficiency and calling attention from across the galaxy. The present dimness does not prove that such phases never occur. It says only that on average the core now lives in a mode where most energy is hidden in motion or carried away rather than radiated. Comparisons with distant active cores sharpen this view. Giants that blaze across intergalactic space often sit in galaxies where cold gas continues to pour inward through recent mergers or through dense cooling halos. Their disks are thick with fuel, their magnetic dynamos are vigorous, their jets punch through the surrounding medium and deposit energy far from the source. The Milky Way is quieter. Its fuel trickles inward through a barred spiral architecture that filters and delays. Its inner cluster bubbles with stellar winds, but those winds drive much of the gas sideways or upward rather than inward. The black hole sits in this weather like a drain with a narrow throat. It pulls with great strength only at the very last moment. Before that, pressure and magnetic structure decide who turns inward and who is turned away. Occasionally a dusty cloud or a disrupted fragment breaks the pattern and the core brightens for a season. Then the base state returns. The restraint has consequences beyond aesthetics. A dim core exerts less direct radiative pressure on its surroundings, allowing the nuclear star cluster and the inner molecular streams to evolve without a constant blast of high-energy light. Feedback still occurs, but it is delivered through winds and weak outflows rather than through a fixed beacon. This gentler mode may help explain how young stars can form close to a massive black hole, and how the central molecular zone sustains its broken ring without being torn apart by continuous glare. The quiet accretion puzzle is therefore not a failure to shine. It is a demonstration of many small balances. The balance between ions that carry heat and electrons that carry light. The balance between inflow that feeds the center and outflow that returns material to the surroundings. The balance between turbulence that stirs and tension that orders. The balance between brief hotspots that shout and a background that whispers. Each balance holds within a range, and each can shift when a new visitor arrives or when the inner field rearranges. The puzzle earns its name because it remains stable enough to be a norm, yet unstable enough to break that norm without warning. In the next layer inward, these balances will play out on orbits so tight that space bends the paths of photons into arcs and rings, and where timing becomes a microscope sharper than any lens, infrared light draws back the veil that dust lowers across the inner sky, and allows the crowded heart of the galaxy to come into focus. Visible wavelengths fail along this path, scattered and absorbed by dark lanes that wind through the bulge, but light with wavelengths of a few micrometers slips through with far less loss and carries news from the hidden center. The first clear views arrive when speckle imaging slices long exposures into many brief snapshots and recombines them to reclaim detail from the restless air. Then adaptive mirrors become the craft of choice, quietly flexing many hundreds of times each second to cancel the atmosphere's tremble and hold a star steady against the night. Large mirrors on high, dry summits adopt these methods and turn toward the core with patience measured not in nights but in years. The nuclear star cluster resolves into a city of points. Massive blue stars gather within a few light years of the center, their hot atmospheres leaving sharp signatures in infrared spectra. Older red giants, cooler and larger, wander among them like lanterns that move at a slower pace. Fainter suns trace the background too many to count in a single field, yet precise enough in combination to measure drift and shear across the inner light years. With careful registration against compact master sources that serve as beacons, observers build a stable coordinate frame and begin to track not only positions but paths, weaving orbits into the map until motion becomes as detailed as light. In that city, the central square holds a glow that does not behave like a star. Near the exact dynamical center, a compact source brightens and fades at near-infrared wavelengths, sometimes rising by large factors within tens of minutes, and then slipping back to a low baseline. The cadence is sudden, steep, and often polarized. During some peaks, the preferred direction of the electric field rotates with time, as if a hot knot in a magnetic field twists while it orbits and then cools. The brightness changes hint at sizes that no ordinary star can claim, and the timing suggests a region only a few light minutes across. On certain nights, a faint rhythm appears in the light curve, a pattern that repeats for an hour or so, and then dissolves, consistent with the small hot spot tracing loops near the innermost stable orbits before shear tears it apart. The flares do not keep a rigid schedule, yet their statistics are not aimless. Their energies gather within a limited range. Their rises are often faster than their falls. Their colors redden as they decay. These traits fit electrons that receive sudden injections of energy and then cool by synchrotron radiation as they spiral along magnetic field lines. Sometimes a modest X-ray brightening follows with a delay, as though a portion of the same electron scatters infrared photons to higher energy through inverse processes. At other times, the near-infrared flare stands alone, a reminder that more than one channel can release stored energy from the inner flow. Coordinated campaigns turn this flicker into a microscope. Ground observatories schedule long runs during seasons of best weather. Space telescopes wait with steady instruments beyond the atmosphere. Millimeter arrays listen for changes in polarization and total flux. High-energy observatories in orbit hold watch for short pulses. When the near-infrared light begins to climb, alerts propagate across the network. If a rotation of radio polarization unfolds at the same time, the event reads like the tightening or reconnection of magnetic fields near the horizon. If a high-energy pulse follows the delay pins down the size of the zone where scattering occurs, if both responses arrive with no delay, the emission regions must overlap closely in space. Each case sharpens the geometry of the inner flow without a single image of its own. A leap in precision arrives when separate telescopes combine their light. Interferometry in the infrared fabricates baselines as long as the distance between domes on the same mountain, and produces a synthesized beam far sharper than any single mirror could deliver. With that beam, the position of the compact near-infrared source can be measured relative to nearby stars with astonishing accuracy. During some flares, minute excursions trace short arcs consistent with a hotspot that loops around the center before dissolving. The sense of rotation and the speed of change line up with the mass already weighed by stellar orbits, and with the expectation that near-horizon paths complete in tens of minutes. On quieter nights, the compact source sits within errors on the same radio coordinate as the beacon known as Sagittarius A, knitting the infrared and radio frames into one. The same instruments refine the demographics of the inner cluster. Infrared spectra add temperatures, elemental fingerprints and wind signatures to the positions and proper motions already in hand. Many bright blue stars look young for so harsh a neighborhood, a surprise so close to so strong a tide. Their presence pushes theory toward disk fragmentation around the center in the past or inward migration by a massive cluster that later dissolved. Some orbits share a family resemblance, their planes aligned in a way that echoes the disk idea. Others are elongated and inclined as though scattering and slow torques have already begun to erase the memory of a single birthplace. Not every change in the field belongs to the engine. Soft knots of dust drift on stretched orbits and elongate as they swing around the center, their emission lines broadening under shear. Some prove to be stars wrapped in cocoons that are slowly stripped by winds. Others may be nearly starless clumps whose light is powered by compression and by local heating as they pass through the inner medium. Whether a knot survives a passage or dissolves places limits on the density and temperature of the hot wind that fills the inner light years. A survivor implies a gentler sea. Fragments and fading tails point to stronger tides and sharper gradients. Infrared polarimetry deepens the diagnosis. The degree of polarization often rises near the peak of a flare and declines as the light fades. The angle rotates in patterns that suggest a field with both toroidal and vertical components, ordered enough to imprint a signature, yet tangled enough to evolve within a single event. These features resonate with rotation measures drawn from millimeter work which limit the column of charged particles and the strength of the field along the line of sight. The combination suggests a magnetized dilute plasma in which electrons gain energy in brief localized episodes and then cool as the field lines and the flow shear them apart. Time keeps serving as a ruler. A flare that doubles and halves within tens of minutes must arise in a region only a few light minutes across. Substructure on timescales of a few minutes demands even smaller zones. A repeating hum that lingers for an hour places the emitter on orbits close to the innermost stable paths. These inferences dovetail with the mass set by star orbits, and with the horizon scale sizes hinted at by very long baseline images at millimeter wavelengths. None of these measures alone would suffice. Together they cross-check and reinforce one another until the picture holds. Long watching also teaches caution. A star that passes behind a dust filament can dim and redden for weeks. A windshell can masquerade as a drifting clump. A calibration source can betray an assumption and paint a false flare. Teams build redundancy into every campaign. Fields are observed in multiple filters. Spectra are taken during peaks to separate line emission from continuum. Reference frames are tied and retied and compared to the radio grid. Patience and method turn a flickering field into a coherent narrative. Cross seasons, the ledger shows patience rewarded. There are months with little more than a whisper. There are weeks when sparks repeat. There are rare times when a wandering clump approaches closely and the rate of flaring climbs. Each episode refines models of how energy is stored and released near the horizon. Each quiet spell reminds researchers that the base state is a low-efficiency flow that carries most of its heat inward or outward rather than radiating it. The combination builds a view in which hotspots, magnetic stress, and sheared plasma set the timing and strength of brief lights against a background that whispers. Infrared eyes therefore accomplish two tasks at once. They map the actors that gravity has weighed, and they watch the stage lights that magnetic fields and hot plasma switch on and off. In doing so, they knit together scales from light years to light minutes, from star clusters to compact knots. They turn dust from an obstacle into a filter and time into a lens. What they deliver is not a single definitive image, but an unfolding sequence in which each flare, each stretched cloud, and each young star offers a new hint about the laws that rule near the point of no return, where the next layer inward will bend not only paths of matter, but also paths of light itself. High above the atmosphere, where air no longer swallows the shortest wavelengths, a different voice from the center speaks in X-rays. Space observatories watch the core against a dark background that stays steady for hours, and what they see is a baseline so faint that it barely rises above the cosmic hush, broken by sudden spikes that climb in minutes and fade in less than an hour. These flares are rare compared with the restless near-infrared flicker, yet when they arrive they declare that particles near the horizon have leapt to extreme energies and released them in a rush. The instruments that open this window are built for patience and for speed at once. One set excels at collecting many photons and spreading them into spectra that show how the brightness changes with energy. Another specializes in timing, counting each arrival with great precision so that rise and fall can be written like a heartbeat. A third reaches to higher energies, testing whether the same outburst continues into a harder band. Together they sketch a portrait of a source that sits near silence, then brightens by large factors, then rests again as if nothing had happened. The light curves climb fast. In a handful of minutes, the X-ray signal can leap from almost nothing to a sharp crest. That climb sets a scale. A region cannot coordinate such a change if it is larger than the distance light can cross in the same time. For the mass at the center, this limit places the source within a few tens of event horizon diameters. The decay often stretches longer than the rise, a shape that hints at rapid heating, followed by cooling that takes more time to drain away. The spectra themselves look like smooth slopes, rather than like a forest of lines, which points to non-thermal processes, rather than to hot, dense gas in equilibrium. Two families of explanations take the lead. In one, electrons gain energy suddenly through magnetic reconnection, the snapping and rejoining of field lines that convert stored magnetic tension into particle motion. Those electrons spiral along the fields and radiate synchrotron light that can reach X-ray energies if their speeds are high enough. In the other, electrons first radiate in the near-infrared, then scatter those same photons up to X-rays through inverse processes. The timing sometimes supports the second path, with a soft lag between the near-infrared peak and the X-ray crest, but at other times the two bands rise together, or the X-rays stand alone without a clear near-infrared partner. The center does not offer a single channel. It offers a web of channels whose relative weights shift with the field geometry and with the location of each event. Polarization adds a clue. During some near-infrared flares, the preferred orientation of light rotates, marking a magnetic structure that changes as a knot orbits and shears. When an X-ray flare coincides, the smooth, featureless spectrum and the short timescale speak for a compact zone where fields are strong and ordered enough to accelerate particles efficiently and to direct their loss of energy into a narrow band of processes. The electrons then cool quickly and the light decays. The near silence between flares matters as much as the spikes. It tells of a base state where electrons do not often reach the energies needed for strong X-ray radiation, or where the gas density is so low that scattering cannot amplify the photons produced at longer wavelengths. Models that feed the horizon with a hot thin flow predict exactly this. Most of the heat remains locked in heavy ions that radiate poorly, and only when magnetic stresses concentrate and release does a small fraction of energy land on electrons and leap out as X-rays. Even beyond the flares, X-rays trace a second, quieter population. Farther from the horizon in the crowded inner light years, the hot, thin plasma created by stellar winds glows with thermal bremsstrahlung, a continuous spectrum produced by electrons jostling through the electric fields of ions. This extended glow is steady on human timescales and reveals temperatures of many millions of degrees. It outlines where the winds of massive stars collide and where shocks heat the medium. It is not the voice of the horizon itself, but the weather that fills the inner environment and supplies the slow background against which flares stand out. Dust along the line of sight adds a subtle effect. Small grains scatter a fraction of incoming X-rays into a soft halo around the point source. During a bright flare, a delayed ring can sometimes appear as scattered light arrives by longer paths, a faint echo that carries a timestamp from the original spike. These echoes serve as accidental rulers. Their expanding rings constrain both the location of dust screens along the sightline and the original flare's timing, a geometry lesson written in scattered photons. In long campaigns, the scarcity of X-ray flares makes each one notable. Some reach energies an order of magnitude above the usual peaks events that hint at especially strong field rearrangements, or at pieces of gas compressed in the innermost flow. Teams attempt to catch them with every instrument at once. If a very bright, near-infrared flare with clear polarization rotation aligns with a hard X-ray spike, the case for synchrotron at the highest energies strengthens, because the same ordered fields would guide both bands. If instead a moderate near-infrared rise precedes a softer X-ray, brightening by a short delay, scattering gains ground. The truth may be that different corners of the inner flow favor different mechanisms, and that the relative importance shifts as the flow tilts, thickens, or thins. Another set of ideas treats some flares as the signatures of small bodies falling inward. A disrupted fragment of rock or ice could vaporize in the hot wind and inject fresh electrons into the field, seeding a brief outburst. This notion is attractive because the inner cluster likely sheds minor bodies over time, and because such events could occur without a large change in the overall accretion rate. Yet the fastest rises and the most ordered polarization argue that at least the sharpest flares are driven from within the magnetized flow itself, where reconnection can reach the needed power on the observed timescales. The brightest spikes also invite speculation about motion near the innermost stable orbits. If a hot knot forms at a radius where orbits close in tens of minutes, the light should show hints of that motion. Small sub-peaks spaced by a characteristic time or a gentle rhythm that fades as shear tears the knot apart. Some X-ray light curves do show such hints, though noise, and the scarcity of photons make them fragile. Future timing with larger collecting areas may tighten those patterns until they shift from suggestion to proof. Meanwhile, every flare already constrains the horizon's neighborhood. No solid surface announces itself with lingering heat after the spike ends. No broad, steady emission follows as if a wall had been warmed. Instead, the light falls back to near silence, in keeping with an engine whose inner boundary does not radiate. The most practical test remains to catch a storm of flares after a known delivery of fresh fuel, perhaps a dusty cloud pulled thin and heated as it skims the flow. If outbursts multiply after such a passage, the cause and effect would tighten, linking inflow field stress and particle acceleration in a chain. Coordinated multi-wavelength campaigns pursue exactly such alignments, banking long hours of quiet watch in exchange for the occasional night when everything happens at once. The outcome so far is a narrative with firm anchors and open questions. The firm anchors are these: the X-ray flares are brief, compact and non-thermal. They arise within a few tens of horizon diameters. They often partner with near-infrared flares. They leave little trace once finished, and they occur against a steady extended X-ray background set by hot stellar winds. The open questions circle the details of acceleration, the role of spin and field geometry, and the balance between channels that send photons straight to X-rays and channels that step them upward from longer wavelengths. Each new flare tests these balances again. Each quiet stretch reminds watchers that hidden energy can move inward without making light. The mystery deepens at the edge of sight, and the path forward is clear: more time on target, sharper clocks, and patient coordination across the spectrum to hear the next brief shout from a place where gravity squeezes everything, even light, into tight curves and short lives. Close to the edge where circular paths shrink to their last stable size and space, itself bends light into loops. The inner flow sometimes knots into compact islands of heat that skim the rim and brighten the darkness with brief ordered signals. These hotspots are not permanent structures. They ignite when magnetic fields wind tight and reconnect, or when compression in a sheared flow pumps energy into a small parcel of plasma. For a short time, the parcel glows more intensely than its surroundings and travels along a near circular track set by gravity, while radiation, shear and expansion work to erase its identity. The result is a light curve with hints of rhythm, a rise as the knot forms a sequence of gentle hums as it circles, and a fade as the knot cools and dissolves. Because these orbits take tens of minutes for a mass of several million suns, and because the path lies only a few times the horizon diameter from the center, timing transforms into a ruler that measures a realm too small to see directly. The signature of an orbiting knot is not only its rhythm but also its changing color and polarization as it moves. When the spot approaches along the line of sight, its light is beamed and slightly blue shifted by the speed of its motion. When it recedes, the opposite occurs. As it passes behind the black hole, lenses of curved space deflect some of its light into arcs that allow part of the hidden side to be seen producing faint echoes and soft shoulders in the light curve. Through one orbit, the preferred direction of polarized light can swing as the knot samples different angles of the local magnetic field, and as lensing and time delay alter which portion of the knot dominates the view. If the field has both toroidal and vertical strands, the swing may be smooth, but not symmetric, a clue to the geometry that shapes the plasma. In some flares, the data approach this ideal. Near-infrared brightness climbs in minutes, then small sub-peaks recur at a spacing of roughly a few tens of minutes before melting into noise. Polarization angles rotate over similar intervals, On a very stable night, interferometric astrometry may even follow the centroid of the light through a tiny arc on the sky, a path so short that it demands instruments capable of weighing motions, as delicate as a grain's drift at the distance of the moon. These patterns suggest a knot circling at radii, comparable to the innermost stable orbits where gravity's grip is tight and time dilates measurably. They do not repeat perfectly because the flow is not a rigid track. It is a living field of stresses where each knot forms at a slightly different place and in a slightly different state of the background. Sometimes the spot endures for several cycles, sometimes sheer tears it apart within one. Even a partial cycle holds value because the spacing between subpeaks and the sense of polarization rotation together limit the radius of motion and the orientation of the path on the sky. The orientation matters because it encodes the tilt of the inner flow and the direction of the central spin. If the spin axis leans toward the observer, the beaming pattern and the polarization swing differ from the case where the axis lies sideways. If the flow tilts relative to the spin, additional precessions enter, shifting the apparent rhythm and twisting the polarization a little each loop. These are small effects laid on small signals, but their combination could eventually reveal whether the black hole rotates slowly or swiftly, and how its spin aims within the bulge. In principle, the period of the hum, once the radius is known, is also a spin probe because the innermost stable orbit depends on spin moving inward for co-rotating paths and outward for counter-rotating paths. In practice, the flow is thick and messy, and knots may orbit at a range of radii that blur the clean mapping from period to spin. Even so, a population of well-measured events could bound the possibilities. Light bending writes further marks. As the knot goes behind the black hole, lensed light can form a secondary image that arrives slightly later than the direct light. This echo is weaker, but not absent. In a very clean flare, a small shoulder after the main peak might be such an echo. Its timing depends on the path length differences set by the curvature of space and the viewing angle. Detecting it robustly would fix both geometry and mass with new precision, because the echo lives so close to the edge that only strong gravity can supply the needed delay. Hotspots also carry information in their spectra. If the electrons radiate primarily by synchrotron processes, the near-infrared emission will be polarized and will fade as the electrons cool. If scattering lifts some of those photons to higher energies, a small X-ray pulse may follow, perhaps delayed by the time it takes for electrons to drift into regions where scattering is more effective. The relative heights of the near-infrared and X-ray peaks then speak to the density of photons, the energy of electrons, and the strength of the field. During a single orbit, the color can drift slightly as the knot moves through patches of different density and field strength, or as compression in the orbital plane tightens the field temporarily. Observers mine these drifts for clues to the pressure balance near the rim and to the distribution of field lines that thread the inner flow. These same events knit together bands. Radiopolarimetry at millimeter wavelengths records slow rotations of polarization angle and changes in the total flux that sometimes line up with trains of near-infrared subpeaks. When a rotation in radiopolarization accelerates during an infrared flare with a quasi-periodic signal, the two bands likely respond to the same rearrangement of field and plasma, with the deeper near-infrared tracing the knot itself, and the slower radio measure tracing the larger volume through which that knot circulates. Coordinated campaigns seek these overlaps the way navigators seek fixed stars, because each overlap ties one model parameter to another and narrows the field of possibilities. Hotspots are fragile storytellers. They form in turbulence. They sit in a bath of shearing plasma that both carries and erases them. They exist on orbits that compress, stretch, and twist according to gravity that grows stronger with each step inward. A small change in the feeding stream, a shift in the pressure of the inner wind, or a jolt in the magnetic configuration can alter the way a spot brightens, darkens, and drifts. The models that predict their behavior therefore come with humility. They are not claims that the inner flow is made of tidy beads on a string, but proposals that when the flow produces a compact overbright pocket, gravity and magnetism imprint on it a predictable rhythm before the pocket dissolves. By gathering many such rhythms under many conditions, observers hope to separate the universal marks of strong gravity from the local marks of weather. The horizon-scale images produced by networks of radio dishes add a final layer to the reading. Although these images are most sensitive to the broader ring of emission, rather than to very brief knots, they do contain fast phases that can in principle respond to orbiting features. Closure phases measured across triangles of baselines shift by tiny amounts when a bright clump moves across the ring. If a near-infrared train of sub-peaks occurs during a radio campaign, with the right coverage matched wiggles in closure phase, could betray a hotspot circling within the broader glow. Combining that astigmatic radio view with the sharp timing and polarization of the near-infrared would turn 3 partial pictures into a single sharper portrait of motion near the rim. In the end, the value of hotspots lies in how they convert a tangle into a metronome. Without them, the inner light would look like noise, a blend of many processes overlapping without a clean phase. With them, the blend sometimes separates into a lead voice and a rhythm section, and gravity adds the beat. The beat is not steady for long, and it changes with each performance, but its presence affirms that plasma can carry information about space and time as surely as stones can carry information about weight. When the next compact knot kindles near the edge and begins its short run, its hum, its colour, and its rotating polarization will again test the size of the last stable paths, the structure of the field, and the orientation of the flow. The knot will fade and the background will whisper, but the trace will remain in the ledger, another small proof that near the horizon of a massive black hole, motion writes itself into light in ways that clocks and careful eyes can read. From time to time, the inner sky receives a visitor that is neither a bright star nor a permanent knot in the hot flow, but a fragile cloud wrapped in dust and gas that wanders inward on a stretched path. Its shape is humble at first glance, a small smear against the crowded field, yet its journey becomes a probe placed by nature into the tide and wind near the core. Years before closest approach, the object moves slowly enough that its light blends with the background. As it falls, its orbit reveals itself as highly elongated a near plunge that will carry it to a distance only a few thousand horizon diameters from the centre. Along the way, it brightens in specific lines of hydrogen that light up when gas is warmed and ionized, and in a soft continuum of dust that glows as grains absorb radiation and re-emit it at longer wavelengths. The path is a countdown. With each season, the image stretches a little more along the orbit and narrows across it the first unmistakable sign that tides are at work. The gravitational field grows stronger with each step inward. Differences in pull between the cloud's head and tail draw it into a string. The shear is not violent enough to tear a star, but it is more than enough to tease apart a loose clump. Spectra add motion to the shape. Ahead of closest approach, the head shows a strong shift towards shorter wavelengths as it falls, while the tail lags behind with a gentler shift. After the turn, the pattern swaps, the head now marching away, and the tail still catching up. The entire sequence looks like chalk dragged through a current, smeared and curved by the flow. At first, many imagine that this will be a test of feeding, A naked cloud should collide with the hot wind that fills the inner light years, raise a bow shock and bleed mass into the accretion flow, perhaps stirring a season of brighter activity. Predictions multiply. Some expect an X-ray glow from the shock. Others imagine a burst of near-infrared flares as fresh fuel rains down. Observers schedule intensive monitoring across wavelengths, hoping to catch an unambiguous link from an inbound clump to an outburst near the horizon. The turn comes and goes. The cloud stretches and fades. The hoped-for storm does not arrive. Flares appear as they often do, but no sustained step-up follows, no long afterglow, no clear jump in feeding. The lesson is not disappointing. It is precise. The lack of a strong response constrains the density of the inner wind and the efficiency with which a small clump can seed the flow. If the medium were denser, the bow shock would have glowed more. If the flow were eager to accept fuel, the light curve would have responded more dramatically. Instead, the inner region behaves as a sparse hot bath that strips and heats the visitor without swallowing much of it at once. The cloud's own nature becomes a second lesson. A purely starless clump should have shredded completely, leaving only a thin ribbon. Yet a compact core persists through closest approach, and the dust emission does not vanish. The object could be a star wrapped in a puffy envelope, perhaps a young star still holding a thick shell, or a product of a stellar merger bloated by heat that will slowly radiate away. In that case, the tides stretch the envelope while the star's gravity keeps the inner layers bound, a design that explains why the object survives the turn and reappears afterward. Similar wanderers have been spotted on related paths in other years, each one adding weight to the notion that the inner cluster regularly tosses small, dusty bodies toward the center. Whether these bodies are stripped parts of circumstellar disks, swollen post-merger remnants, or nearly starless clumps, they all serve as test masses that carry built-in thermometers and barometers. How much they brighten tells how strongly the hot wind rubs them. How closely they survive tells how sharp the tides become at each radius. How quickly their lines broaden and narrow tells how the velocity field varies along the orbit. Even their absence of dramatic consequences is a clue, because a quiet aftermath pushes models away from dense high-pressure inner media and toward lighter, more stratified states. Drag becomes a quiet sculptor. As the cloud glides through the hot plasma, it surrenders momentum to the medium. The effect is small but detectable across years. The pericenter distance shifts by a little. The timing of the return changes by a little, and the shape of the tail records where drag is strongest. Combined with the measured tides, this drag constrains the pressure and density structure of the gas inside a light year. The result is a map of an invisible weather system drawn by the fading trace of a single traveller. The same traveller acts as a die for magnetic fields. Polarization measurements of its emission reveal changes as the cloud crosses regions where fields are more ordered. If a bow shock forms the field ahead of the head, may align, raising a measurable polarization that then rotates as the geometry changes. If reconnection events occur in the wake, a brief localized flare might ride along the path, a small echo of the larger flares from the horizon, but tied in space to the cloud's own footprint. Observers scan for such signatures and sometimes find hints short brightenings that trail the object, and then vanish too small to claim as proof, yet suggestive enough to shape follow-up strategies. These clouds also test how sharply the accretion flow is bounded. If the inner hot plasma forms a thick pressure-supported structure, a passing envelope may skim the surface and leave ripples without penetrating deeply. If the flow includes thinner streams threaded by strong fields, the envelope might be peeled into filaments that follow those lines for a time before they mix away. In either case, the lack of a bright, long-lived response argues that the last step into the horizon remains a bottleneck narrow enough that most inbound material must be prepared by many smaller exchanges before it can pass. The narrative is not identical for every visitor. Some approach on paths with larger angles to the plane and sample different heights within the stratified inner atmosphere. Some carry more dust and show stronger thermal emission. Some arrive as pairs or small groups, perhaps remnants of a once larger structure that has already been torn into pieces. Each variation adds a tile to the mural. One object demonstrates that a bloated stellar core can survive tides that shred a loose clump. Another points to a limit on how dense the hot wind can be without producing a shock bright enough to see. A third hints that the orientation of inner magnetic fields changes with height. Together, the variations demonstrate that the center's weather has layers, that the feeding pathway has steps, and that time near the core is written not only in flares, but also in the slow fading of stretched dust. A final sobering lesson arrives in the scale of patience required. The cloud's infall takes years. The careful alignment of instruments must span seasons. The changes that matter most are subtle: a small change in line width, a slight rotation in polarization, a faint re-brightening that follows the head by a measured delay. The absence of a dramatic outburst is itself a data point that earns its place beside the few loud nights when the core shouts. In this way, the wandering clouds teach an ethos as well as physics. They show that near a massive black hole much of the action is in what does not happen, because the inner flow wastes little swallows slowly and releases most energy only in tightly confined moments close to the horizon. The visitors depart thinner, elongated, and dimmer, having written their stories into the inner map. The engine remains as it was quiet on average, bright in brief sparks, and all the more mysterious for having turned aside an invitation to blaze. Yet those sparks carry the same signatures that the cloud has tuned, and when the next flare climbs, the near-infrared and the X-rays, the parameters it implies for size, density, and field, will rest upon the calibrations that the wanderers provided. A fragile smear has earned the power to weigh the unseen, and a faint echo has become a ruler for a gravity that does most of its work in silence. Threads of magnetism lace the inner galaxy, faint and stubborn lines that reveal themselves only when special light gives them away. Radio maps at longer wavelengths show narrow filaments that stand almost upright against the general grain of the bulge, tens of light years long and very thin, as if stretched taut by forces stronger than the surrounding turbulence. Their emission is non-thermal, the sign of electrons spiraling along ordered fields and shedding energy as they go. These filaments cross the busy background like strokes of a fine brush on rough canvas. They do not point directly at the core in every case, but their presence so near the center argues that magnetism there is not a minor decoration. It is architecture. Closer in within a few light years, polarization carries the argument into the hot flow itself. At millimeter and submillimeter wavelengths, the compact source shines with a polarized light that twists as it passes through magnetized plasma along the line of sight. The amount of twist varies with frequency, in a way that ties the rotation to the product of field strength and charged particle density. The measure changes with time, a sign that the inner flow rearranges itself from week to week and season to season. During some near-infrared flares, the polarization angle rotates even while the brightness rises and falls, as if a knot of hot electrons rides a track through a field that has both toroidal lines wrapped around the flow and vertical lines threading it, a braid that evolves as the knot orbits and shears. In such a field, angular momentum can be shuffled outward without the clean spiral shocks of a dense disk, and energy can rise and fall in places where the lines reconnect and release their tension. The same magnetic order that guides electrons to radiate also helps to decide who gets to approach the horizon. A puzzle lies here. Many black holes of similar or greater mass in other galaxies launch narrow jets that shine across enormous distances, beams that mark strong magnetic fields anchored in a fast spin and fed by steady disks. The center of the Milky Way shows no such persistent jet. There are hints of small outflows and faint features that could be the footprints of collimated motion, but nothing like the bright lances that cross intergalactic space. The likely reason is simple, and telling the diet is thin, and the flow thick so the field never builds the coherent high-pressure structure needed to hold a jet open. Instead, magnetic stresses fling part of the inflow back as a broad wind. That wind carries mass and angular momentum outward, and sneaks energy into the surrounding medium without declaring itself as a narrow beam. The evidence for such winds is circumstantial but layered. The total light from the compact source sits far below what a bright thin disk would produce, at a similar feeding rate a gap explained if much of the available mass never reaches the horizon. Line ratios and temperatures in the inner light years point to hot dilute plasma, with a pressure profile that declines more gently than a purely inward flow would allow a hint that energy leaks outward. Changes in Faraday rotation during near-infrared activity suggest that field lines inflate and relax as events occur, a breathing that suits a flow that both receives and rejects material. On wider scales, structures above and below the plane cast long shadows of past outflows. The inner bulge holds arc bubbles and curved ridges that glow at radio and microwave wavelengths, and farther out giant lobes of high-energy emission reach high above the disk and deep below it. These lobes need not be sustained by a present jet. They could be the memory of episodes when the center and the surrounding star formation both pushed energy into the halo. Whether or not the compact source directly drives the larger structures, the pattern near the core is clear winds matter. They shape the weather in which clouds stretch, in which hot spots rise and fade, and in which young stars keep their shells. They also close the loop between feeding and restraint because the same stresses that rob gas of its spin and help some of it to fall can throw other parcels back, thickening the surrounding medium and softening the inflow. Within a few tenths of a light year, where the plasma turns fully ionized and the temperature soars, the flow takes on the character of a magnetized pressure-supported torus. Here, turbulence is not the random jostle of a dense fluid, but the choreography of field lines that tangle, tighten, and reconnect. Viscosity is not a molecular constant, but an emergent effect from waves and instabilities that pass momentum across the flow. In this regime, even the definition of a surface blurs. There is no hard boundary between the torus and the surrounding wind. Patches peel away and rise like steam guided by the field and by buoyancy. Other patches slide inward along channels where magnetic tension aligns the motion. When a flare brightens the near-infrared, and the X-rays the local field appears to have pinched and snapped heating electrons that then shed their energy as light. When the light fades, the field relaxes and the wind resumes its soft lift. The absence of a steady jet does not mean an absence of direction. The polarization pattern on the smallest radio images hints at a preferred orientation for the inner field, a rough axis along which stresses can build more easily. If the black hole spins as most do, then the spin and the field together define a natural frame. In a system with a thin, bright disk, that frame becomes the spine of a jet. In this system, with a thick, underfed flow, the same frame may merely tilt the wind, making it stronger above and below the plane than within it. Over long time, such a preference could help inflate the larger lobes that stand far from the disk. Over short times, it would tilt the paths of small ejections and faint arcs. The nuclear star cluster complicates this picture with its own winds. Massive stars launch fast streams that collide and heat the inner light years to millions of degrees. Those streams feed the hot bath and blur the line between the black hole's outflow and the cluster's weather. Yet, the two are not the same. The cluster produces a more isotropic froth, its bubbles rising and merging in all directions. The black hole's contribution is tied to the field geometry of the inner torus and to the timing of events near the horizon. Where the two meet, structures arise that combine both characters' arcs that reflect stellar wind pressure and subtle alignments that betray magnetic guidance. Observers peel the two apart by watching how features respond to flares, how polarization rotates across frequency, and how the pressure profile changes with radius. The combined results argue that the inner engine influences the broader zone less by raw luminosity than by sculpting the paths along which energy escapes. It is a sculptor of routes rather than a lighthouse. When a dusty cloud approaches, this sculpting decides whether the envelope drags hard and glows or skims and fades. When a hot spot forms, it decides whether the knot drifts outward along an aligned channel as it cools or dissolves in place. When the baseline brightens for a week, it decides whether the added light reflects a general warm-up or a rearrangement that redirects energy without raising the total very much. In this way, the magnetic order that fails to produce a grand jet still rules the traffic of heat and motion close to the core. Such control extends to the smallest scale that observations can yet probe. Very long baseline campaigns at the shortest radio wavelengths now recover not just a blurred ring, but hints of ordered polarization around it, implying that the emission near the shadow of the horizon is threaded by coherent fields. The pattern resembles the swirl seen around a far larger black hole in another galaxy, though the details differ in ways that match the lower feeding rate and the different environment. The comparison suggests a unifying theme when fuel is plentiful fields and spin collimate jets. When fuel is scarce, the same ingredients inflate winds and redirect energy quietly into the host. The center of the Milky Way sits in the second mode, and its subdued light masks a great deal of magnetic work. The intrigue deepens because each piece of this story invites a measurement that only patience can supply. More seasons of polarization monitoring will show whether the inner field holds a long-term orientation or wanders, whether rotations prefer one sense, and whether rotation speeds correlate with flare strength. Deeper imaging of the non-thermal filaments will chart where the longest strings anchor, and whether their foot points drift as the inner engine breathes. If a stronger feeding episode ever arrives and the core brightens for months, the response of the field will reveal whether this engine can under pressure lift a true jet for a time, or whether its nature is to refuse that path and keep sculpting winds instead. Until then, the quiet breath continues a slow exhalation and inhalation of magnetized plasma that carries energy away from the horizon without fanfare, leaving the stars to write the mass and the dust to write the boundaries while the fields write the rules. Coordinated campaigns knit the inner story together by turning many instruments into one patient eye. At radio and millimeter wavelengths, very long baseline interferometry links dishes separated by thousands of kilometers into a single synthetic aperture with the angular sharpness to probe horizons. The Earth itself becomes a moving spacer that rotates baselines through many orientations during a night writing curves of response that encode the source structure. Clocks at each station keep time with exquisite precision receivers, cool their electronics until thermal noise falls to a whisper, and recorders pour torrents of bits onto storage that later travel by aircraft to central facilities where the signals are combined. The work looks simple once the images arrive, but the true scene is made in the planning. Weather matters because water vapor trembles the phase of short waves and shortens the time over which signals remain coherent. Windows are chosen when dry air settles over summits and plateaus. Telescopes at high altitude in South America, in North America, in Europe, in Hawaii, and at the South Pole prepare to listen together, ready to catch a few hours of global clear sky that may not repeat for a year. The network called the Event Horizon Telescope gathers these stations, and when conditions align it turns them toward the center. Sagittarius A star is a challenging target for this method because it is small on the sky but restless in time. In distant galaxies with larger black holes light near the horizon, it takes many hours to change, so an observing night records a nearly static scene. At the center of the Milky Way, the innermost orbits complete in tens of minutes, so the region brightens and dims during the same hours that the Earth rotates the baselines. Static imaging would blur a lively ring into a smear. The response is to treat time as an axis of reconstruction. Instead of forcing the data to tell a single still story, algorithms ask it to tell a short movie, regularized by physics and by experience with simulated flows. Closure quantities that are robust against atmospheric corruption, such as closure phases and closure amplitudes, carry the strongest hints. Their small drifts over minutes become clues to compact bright features circling within a broader ring. When many stations survive the weather together, the pattern of these closures tightens into constraints that demand a ring of emission, roughly the size gravity predicts for the mass already measured by stellar orbits. Polarization enters as a second layer. Receivers record not only total power, but also the orientation of electric fields. After careful calibration, the interferometer recovers a map of polarized structure around the ring. The pattern is not random. Vectors swirl in an ordered fashion, implying magnetic fields that thread the near-horizon plasma with coherence over the scales that produce the light. This polarization ring is a cousin to the pattern seen around a much larger black hole in a distant galaxy, but it shows differences that match the thinner diet and faster variability of the Milky Way's core. In this way, magnetic order becomes a shared language across scales while feeding rate and environment-determined dialect. The line of sight toward the center also carries a liability. Irregularities in the ionized medium between the bulge and the Earth act like a rough lens, scattering radio waves and blurring images at longer wavelengths. The effect weakens as frequency rises, so the campaigns push to the shortest wavelengths that the atmosphere and technology can bear. Even then, the scattering must be modeled and removed lest it shoves small features into the wrong places. Astronomers test the models by applying them to compact calibrator sources near the core, and by checking for consistency across independent reconstructions. The agreement is never perfect, but the broad ring and its polarized swirl persist across methods, epochs and teams. Timing networks on the ground and in space watch alongside the baselines. Near-infrared telescopes armed with adaptive optics track the compact variable source and raise a flag when brightness begins to climb. Space-based X-ray observatories keep a steady watch on the same field. If a flare rises during a radio campaign, the temporal overlap becomes gold. A rotation in radio polarization that accelerates during a near-infrared flare with substructure argues that both bands respond to the same rearrangement of field and plasma. A delayed X-ray crest suggests that some of the new infrared photons are being lifted to higher energies by scattering. If no high-energy response follows, the event may have heated electrons only modestly, or it may have occurred in a region too thin to scatter efficiently. In either case, the crossband pattern tightens the size and location of the flare site within the broader ring the interferometer sees. The pace of this work is slow by design. The network schedules a few days each year, waits for weather, observes through the night, then spends months to years on correlation calibration and reconstruction. Teams swap algorithms and blind test each other's outputs to guard against shared bias. The goal is not to produce a pretty picture once, but to build trust in the method until it becomes a ruler that future episodes can lean on. The result is a growing stack of epochs that can be compared. On some nights, the ring appears slightly brighter on the side where material approaches the observer, a trait expected from beaming in a rotating flow. On others, substructure hints at a compact knot that moves a short distance over tens of minutes. These changes are small, but they add up to a portrait of a living rim rather than of a frozen crest, a portrait that matches the restless near-infrared light curves and the rare X-ray spikes. The campaigns also tie the radio world to the stellar map. The compact radio centroid aligns with the focus of the fastest star orbits within tight errors, welding the dynamical and imaging frames. Massa beacons in nearby clouds serve as pegs that fasten the coordinate grid across bands, with each fastening the mass from stellar dynamics and the size from horizon scale. Imaging tighten their handshake. This handshake matters because it underwrites every speculative step taken deeper into the physics of the inner flow. A special challenge arises from the very success of the timing microscopes. When hotspots hum and polarization angles rotate on timescales of minutes, the interferometer must choose between integrating long enough to achieve sensitivity and slicing the night into short enough intervals to follow the dance. The compromise is to build dynamic reconstructions that assume continuity from minute to minute and penalize wild changes that the data do not demand. Early trials suggest that this approach can recover a moving feature without erasing the ring, though the confidence grows only as more nights add their weight. The future promises sharper ears. New stations join the network and extend baselines into directions that were thinly sampled. Wider bandwidth increases sensitivity. Receivers and backends grow more stable. Techniques improve for calibrating polarization across the full chain from sky to recorder. At even shorter wavelengths, space-based interferometry could one day lift the baselines above the atmosphere entirely and push resolution to scales that could follow hotspots through multiple orbits in real time. Meanwhile, ground-based arrays add single-dish polarization maps at millimeter and sub-millimeter bands that monitor the daily mood of the inner flow-catching rotations and swings that can be compared with the rarely scheduled horizon-scale nights. All of this effort meets the same quiet engine whose baseline glow remains low. That quiet is an ally. It allows small changes to stand out. A modest rise in total flux during a campaign can mark a rearrangement of field lines rather than a huge surge of fuel. A brief asymmetry in the ring can point to a passing knot rather than to a permanent crescent. The absence of a strong jet removes a bright distraction and leaves the ring and its polarization to carry the message. Thus the campaigns are not one experiment but a tradition, a yearly habit of listening with many ears for a heartbeat that changes with the health of a thin, hot, magnetized flow. They embody the method that the center demands long patience, sharp clocks, shared frames, and a reluctance to hurry conclusions. In exchange, they've delivered a sight of the near horizon itself, a ring whose size matches the mass weighed by stars, a swirl of polarization that announces ordered fields and flickers that refuse to be entirely smoothed away. The instrument that matters most in this account is not a single dish or a single mirror, but the decision to make them speak together across continents and bands until the invisible center draws its own outline in light. Time becomes a microscope near the center, a tool that reaches scales too small for any present image by turning delays, rhythms, and echoes into rulers. The principle is simple and profound. Light cannot rise, curve, cool, or scatter faster than the rules of space and matter allow. When a flare climbs in a handful of minutes and then softens in a longer sweep, the rise sets an upper bound on the size of the engine that sparked it, while the fall encodes how quickly particles lose energy or drift away. When two bands brighten together or with a measured lag, their separation in time sketches the distance between layers of the flow and the channels by which photons or electrons travel from one to the other. When a faint shoulder trails a peak by a predictable number of minutes, a lens carved by gravity or a veil woven by dust has added a second path, and the extra time stamps the length of that detour. Each of these patterns turns the clock into a lens that resolves what a single snapshot cannot. The light curve of a near-infrared flare shows this most clearly. A sudden steep rise implies heating or compression in a compact region only a few light minutes across. The sharpness of the crest limits smearing by relativistic time dilation and by orbital shear, thereby fixing the knot near a radius where orbits close in tens of minutes for a mass of several million suns. If a faint hum repeats with a roughly constant separation between sub-peaks, a compact hotspot circles for 1 or 2 rounds before dissolving, and the spacing between the hums becomes an orbital ruler. A rotation of polarization that tracks those sub-peaks adds a second independent clock that ties the rhythm to a coherent magnetic geometry. Crossband timing adds depth. When a near-infrared peak is followed by an X-ray crest after a short delay, the lag implies that some electrons first emit low-energy photons, and then lift those same photons to higher energies by scattering, a process that demands a certain density of photons and a certain distribution of electron energies. The measured delay thus bounds both numbers and fixes whether the scattering occurs near the same radius as the original flare or in a slightly different zone. When the two bands rise together without a lag and then decay together, the timing supplies evidence that the X-rays arise directly from very energetic electrons, radiating in strong magnetic fields with little role for scattering. In either case, the timestamp rules out large slow volumes and insists on compact engines. Sometimes the clock reveals a second voice hidden in the first. A near-infrared peak that ends with a soft shoulder, a few minutes later may be the signature of light bent around the black hole into a secondary image that arrives after a longer path. Such a gravitational lens echo would be weak and easily mistaken for noise, but if it recurs with the same separation in multiple events, it becomes a measurable delay that depends on the mass and on the angle of view. Detecting such an echo would let observers tie the geometry and mass with new precision, because the delay is set by curved space itself, rather than by the uncertain behavior of plasma. A more distant dust echo writes longer delays. X-rays from a bright flare scatter off grains along the line of sight, forming a soft ring that expands with time. The apparent growth of that ring acts like an hour hand that points to the location of the dominant dust screen between the bulge and the Earth. When such a ring is detected and timed, it turns a nuisance into a ruler refining extinction maps, and allowing the direct flare light to be corrected for scattering that would otherwise bias its shape. Timing also excavates structure in chaos. The inner light curve is dominated by red noise, a restless variability with more power on long timescales than on short ones. Within that restless sea, quasi-periodic features occasionally surface. Statistical tests then ask whether a cluster of sub-peaks at near equal spacing rises above what red noise could mimic. When the answer is yes, the implied period again points to orbital motion, close to the last stable circles with any slow drift in period, hinting at a change in radius as the knot shears and dissolves. Power spectra and structure functions which compress the light curve into a distribution of variability across timescales reveal breaks at characteristic times. These breaks often land near the orbital periods inferred by other means, and near the cooling times of the radiating electrons, thereby stitching the stories together. the time microscope extends to stellar orbits as well. Around closest approach, the clock of a fast star does double duty. The star speeds up and slows down as it moves along its ellipse, and that change writes a precise schedule that can be compared with predictions. Meanwhile, its light descends into and climbs out of the deep central potential gathering gravitational redshift and special relativistic time dilation that together tilt the measured spectrum over a window of weeks to months. Matching that tilt in phase and amplitude confirms that gravity near the center behaves like a point mass, and it refines the mass itself. Small deviations from schedule then become clues to additional tugs, perhaps from a thick population of dark stellar remnants, or from the mild precession expected in a strong field. Even the horizon scale interferometer uses the clock. Closure phases measured across distant baselines change by tiny amounts when brightness, lopsidedness moves around the ring. Slicing a night into short intervals and regularizing the evolution across them turns those drifts into a time series that can be compared with the beats seen in the near-infrared. If a near-infrared train of subpeaks is accompanied by a gently rotating asymmetry in the ring on the same schedule, then the two clocks read the same orbiting knot through different windows. The agreement in phase and drift would fix the radius and the viewing angle with a fidelity that a single band cannot achieve. Radio polarization adds a slower clock. The rotation measure, which tracks the twist of polarized radio light as it crosses a magnetized plasma, drifts over days to months, correlating its changes with the occurrence of near-infrared, and X-ray flares separates lasting rearrangements of the inner field from transient injections of energy. A gradual swing in rotation measure, without many flares, points to a quiet structural change, perhaps a warp in the inner flow. A flurry of flares with only brief reversible twists points to local reconnection events that do not alter the large-scale field. These associations turn low-cadence monitors into barometers of the inner weather. Timing also enforces humility. Calibration mistakes can mimic lags and red noise can feign a hum. For that reason, the campaigns adopt blind analyses and require that clocks agree across sites and methods before a claim stands. Delays must recur across events and instruments. Periods must survive tests against false positives. Echoes must match the geometry they imply. This discipline is slow, but it converts fragile patterns into measurements that carry weight. Where does the clock point next? Larger collecting areas in space will time the faintest X-ray flares with better precision, reducing the ambiguity between direct high-energy radiation and scattering. Faster readouts and steadier adaptive optics on the ground will track polarization rotation through entire near-infrared events, transforming hints of orbital geometry into maps of field structure. Expanded very long baseline arrays at shorter wavelengths will make dynamic reconstructions with minute cadence plausible, allowing closure phases to follow a knot for several cycles. With those steps, time will sharpen until the near-horizon realm yields periods, echoes, and lags that can be layered into a single consistent model. Even then, the clock will not end the mystery. It will refine it. The delays will settle mass and geometry. The hums will place the rim. The echoes will sketch the curved paths that only strong gravity can draw. What will remain open is how the inner flow chooses when to light a knot, and when to let energy slip inward unseen, and how small changes in feeding tilt the balance between flares and quiet. In that open space, time will continue to serve as the most honest microscope, patient and precise, turning minutes into maps and hours into portraits of a realm where light itself keeps the books as it runs the last tight curves toward the point of no return, Gravity near the center is patient, and its meals arrive on a schedule set more by chance than by need. Most days the engine takes in thin plasma that carries more heat than light. Most years it brightens only in brief sparks when magnetic tension snaps. Yet the same gravity that allows long quiet also sets the stage for rarer, heavier courses. A star on an unlucky path can drift into a zone where tides overwhelm its cohesion. If the star crosses the threshold within which the difference in the central pull across its diameter exceeds the star's own grip, tides draw it into a stream. For a compact sun like the Sun, this tidal distance lies well outside the horizon of a black hole, with several million times the mass of the Sun, so disruption is possible without a direct plunge. The outcome depends on angle, spin, and structure. A shallow approach may only peel away outer layers in a partial event, leaving a core that departs on a changed orbit and returns lighter in a future pass. A deeper approach can shred the star entirely, wrapping its gas into a long ribbon whose front and back race along different paths. Some of that ribbon remains bound and later rains back upon the center, while some leaves forever. The bound part does not arrive all at once. It returns in a cascade, fastest from the tightest loops and slower from the longer ones. As it falls, its shock circularizes heats and can light the center for months with a glow far above the usual baseline. In distant galaxies, such flares have been seen rising swiftly and then fading as the rainback slows. At the heart of the Milky Way, no unambiguous stellar shredding has been caught in the act. The rate is low because the inner cluster is hot in the dynamical sense, and orbits are already mixed. Most stars never wander close enough, and those that do only rarely meet the precise aim that tides demand. The absence of a modern feast does not mean that meals never occur. Over the lifetime of the galaxy, a few disruptions could have happened, each adding a small fraction of a solar mass, and each briefly lifting the inner flow into a brighter, thinner state before it cooled and thickened again. Hints of past activity linger far from the plane, in the form of large lobes that remember energy injected long ago. Whether those memories came from a star's death from a heavier inflow, or from a concert of many smaller outbursts, remains open. Tides do not only reshape stars, they also sculpt the traffic of compact remnants and small bodies. The inner cluster harbours black holes left from earlier generations of massive stars, as well as neutron stars and heavy white dwarfs. Over long times, these dense objects sink inward through many weak encounters that trade energy with lighter stars. Some will pass close enough to the giant at the center to feel large bursts of gravitational radiation. A few will spiral all the way into the horizon in events called extreme mass ratio inspirals. These encounters are too quiet in light to announce themselves across the spectrum, but they will sing in gravitational waves that a future space-based observatory can hear. The rate of such inspirals depends on how crowded the innermost tenths of a light-year are, with remnants a number that the slow drifts in stellar orbits, and the statistics of near collisions may eventually fix. When those waves are recorded, they will carry precise maps of the space-time near the horizon, including the spin of the central mass and the geometry of its deepest potential. Gravity also handles outbound traffic. A close three-body interaction between a star bound to the center and the black hole can fling the star outward at many hundreds of kilometers per second, freeing it from the galaxy entirely. These hypervelocity stars have been seen in the halo, and their existence points back to the central well as a slingshot. Each ejection robs the center of a possible future meal, but adds to the story of how orbits exchange energy, when one partner is so heavy that it acts as an anchor. The slow balance among infill disruption in spiral and ejection sets the growth of the black hole over cosmic time. For a mass of several million suns to have assembled by now, a mix of channels must have contributed. Early in the galaxy's life, when gas was richer and mergers were more common, the centre may have fed more readily, perhaps shining as a modest active nucleus for brief epochs. Later, as the bar and ring architecture matured and the gas supply thinned, feeding likely slowed to the present trickle. The measured mass today fits a history in which steady low-level intake dominates, while rare bright events add punctuation. Even crumbs leave marks. A small asteroid or comet stripped from a passing star can survive long enough to skim the hot inner wind and evaporate. The energy released by such a fragment is tiny in absolute terms, but can still produce a brief near-infrared spark if the fragment encounters a pocket of denser plasma or a region where fields concentrate. The statistics of the faintest flares may include contributions from many such minor bodies, while the brighter flares arise from magnetic reconnection in the flow. In this way, the ledger of light records both crumbs and larger sips, without revealing them as separate lines. Partial disruptions hold special interest because they bridge daily weather and rare feasts. When a puffed envelope from a bloated star skims tides near the limit, a stripe of gas can be torn free without erasing the core. The core departs and may return years later with a smaller mass and a thinner shell. Each pass feeds the centre a little while building a family of stretched streams that later mix into the inner medium. The lack of a dramatic rise after a well-tracked cloud's close pass supports the idea that many such near misses end in modest stripping rather than in catastrophic feeding. The cluster itself shapes how often candidates for disruption appear. If star formation near the centre occurs in disks that later dissolve, the resulting orbits may retain a mild alignment for a while, changing the probability that a member drifts into the lost cone, the set of paths that cross the tidal radius. Encounters among stars then scatter them, filling or emptying that cone, at a rate that depends on the density and velocity dispersion of the cluster. Careful long-term monitoring of orbital orientations may therefore forecast whether the next few centuries favour a higher or a lower chance of a deep pass. The role of spin in all of this remains one of the more potent open questions. A rapidly rotating black hole drags space around with it near the horizon, an effect that moves the last stable orbits inward for matter that co-rotates, and outward for matter that counters the spin. The same dragging may tilt how disrupted debris settles and how easily streams circularize. If future timing and horizon-scale polarization pin down the spin, and its orientation models of partial and full disruptions can be tuned to the local rules rather than to generic cases, the next strong test would be a bright accretion episode caught from start to finish. A dusty or gaseous object approaching on a near plunge could be watched through its turn, its stretching, and the expected rainback. If the near-infrared and X-ray bands rose in a pattern that matched the fallback rate, and if horizon's scale radio phases showed a strengthening and partial flattening of the ring during the same months, the link between tidal feeding and observable response would tighten beyond plausible doubt. The absence of such a feast so far is not failure. It is simply the arithmetic of rare events at a single site watched for a short span compared with the life of a galaxy. Until such a meal arrives, the centre continues to grow, mostly by the slow conversion of hot winds and by the occasional small delivery from a passing stream. The present mass and the quiet light together say that this path, though stingy, has sufficed. The intrigue lies in imagining the moment when restraint breaks. One star torn thin, one disk fragment pulled deep, one compact remnant led into a final spiral, and the quiet heart would change voice for a while. The ring would sharpen, polarization would stiffen, flares would crowd closer together. Then the engine would cool and slip back into its soft underluminous mode, leaving just enough added mass to tip the balance of the next century's orbits by an immeasurable degree. Long famines, rare banquets, and many crumbs. This is how a massive black hole in a calm spiral galaxy likely grows, and this is how the centre of the Milky Way carries on, patient, hungry, and quiet, with the conditions for drama always near, and the decision to remain modest made anew with each piece of matter that reaches for the last tight turn. At the edge of knowledge, the centre of the Milky Way stands both measured and mysterious, a place where mass, size, and position are fixed with care while character remains open. The most direct questions gather around spin. A rapid rotation would tug space around near the horizon, and draw the last stable circular paths inward on the side that turns with the spin, while a slow rotation would relax that tug and push the rim outward. The difference decides how close hotspots can circle before they fall, how strong time dilation becomes along their tracks, and how sharply curved space bends their light into echoes. Spin also sets the scale for precession, a slow twist of tilted flows and of orbital planes that could shift the rhythm of near-infrared hums and bias the direction of weak outflows. If the spin axis leans toward the observer, beaming would brighten one side of the ring more often, and rotate the preferred angle of polarization in a way that repeats across seasons. If the axis lies sideways, asymmetries would prefer another quadrant and echoes would land with different delays. The measurement is within reach because clock's polarization and horizon scale structure all feel the same hand, yet it remains unfinished because the inner flow is thick and restless, and because each flare samples only a small patch of the stage. Another open ledger concerns feeding history. The present light curve says that the engine now lives in a low efficiency state, in which heat rides inward rather than leaving as radiation a regime where ions carry most of the energy, and where magnetic stress lifts much of the inflow back outward as a wind. Yet the inner galaxy carries signs of stronger outflows in the past, from arc bubbles near the bulge to giant lobes that rise high above and deep below the disk. Whether those memories came from the black hole itself during a brighter phase from the nuclear star cluster, during a burst of formation, or from both acting together remains unsettled. A decade of quiet does not erase 1,000 centuries of weather. The search therefore extends to fossils-age synchrotron light that still glows where a wind once ran dust that keeps the imprint of a shock front, or a population of high-speed stars that remember a stronger slingshot. If the center brightens for months or years in the future, and then relaxes, the change would weigh the ladder between faint wind and modest flare state, and would teach how easily the engine can climb it when fuel briefly arrives. The balance between the cluster and the engine forms a third vein of questions. Winds from hot massive stars fill the inner light years with thin hot plasma that both feeds and hinders the black hole. The stars deliver material and stir turbulence, yet they also supply pressure that redirects much of the flow outward and sets a floor to the temperature. The number, ages, and orbits of these stars decide the character of the bath. If starbirth occurs in a disk that later dissolves a mild alignment among planes, can persist for a time and change the supply of gas and small bodies that approach on low angular momentum paths. If inward migration by a cluster dominates, the deposit of young stars could arrive with a different spread of energies and tilt. In both cases, the cluster's weather writes the initial conditions for the inner flow, and the engine edits those conditions by returning energy as a wind, so that cause and effect circle each other in a long exchange. Magnetic architecture threads every layer of that exchange. On horizon scales, polarized maps already reveal ordered fields wrapped around a ring of emission, a pattern that says the near edge is not only hot but organized. On light-year scales, long radio filaments stand almost upright against the grain of the bulge, as if pegged to a tall frame that crosses the crowded central light. What remains to be drawn is the continuous stitch from one to the other, a proven path by which fields in the inner torus seed the field in the wind, and then the field in the tallest filaments. Coordinated monitoring of polarization across wavelengths tied to the timing of flares and to slow drifts in rotation measure promises that stitch. A rotation that speeds during a near-infrared hum likely reports a local tightening of the field. A rotation that drifts for months without many flares likely reports a structural breathing in the torus. If one sense of rotation dominates over many seasons, an axis quietly announces itself. Even the dark inventory remains uncertain. The inner tenths of a light year likely hide a crowd of stellar mass black holes, neutron stars, and heavy white dwarfs left from earlier generations. Their numbers affect how orbits of visible stars process how often close passages occur and how many compact objects feed the central mass through inspirals that produce slow, pure waves in space and time. A future observatory in space that listens for low-frequency gravitational waves will hear those songs, and each one will carry the spin and the geometry of the deepest potential in a code that light cannot copy. Meanwhile, the fastest visible star orbits continue to test for small drifts that could betray a heavy swarm near the core, and near misses continue to set limits on how many remnants can share such a small space without leaving marks. A broader set of questions asks what role a quiet, underfed black hole plays in the long evolution of a spiral galaxy's core. A roaring engine sculpts its host through jets and hard light. A faint engine sculpts through magnetized winds and through the slow influence of gravity. It stirs the hot bath that surrounds it, seeds turbulence that affects how clouds collapse, and quietly ejects high-speed stars that carry energy and metals into the halo. It focuses or deflects inflows guided by the bar and by the broken molecular ring, and it offers a stable weight that sets the tempo for the nuclear cluster. The extent of that influence is hard to measure because the feedback is not a blast, but a shaping of routes, a redirection of heat and of motion along preferred lines. Long monitoring of pressure profiles and of temperature gradients inside the central molecular zone, paired with the slow statistics of flares and the orientation of non-thermal filaments, may finally credit the engine for changes that now seem like weather. Answers will arrive as instruments learn to braid time and space more tightly. Better clocks at high energy will time the faintest X-ray flares and separate direct synchrotron light from scattered light. Sharper infrared interferometry will follow hotspots around Full Circle's map, rotating polarization through entire orbits, and catch lens echoes bent by gravity. Wider and drier radio networks will recover dynamic rings with minute cadence and map polarized structure without smearing. Long baselines of rotation measure will distinguish structural breathing from local knots. Year by year, the stack of matched epochs will grow, and patterns that look like single events will settle into habits that models can hold. Until then, the center remains a paradox that speaks softly. It weighs as a giant and shines as a dwarf. It sleeps most nights and yet sets the pace for a crowded core. The nearer the gaze moves to the horizon, the wider the mystery grows because every new anchor tightens mass and size, while inviting fresh questions about motion field and time. The map now reaches to the last light minutes, but the legend is still being written. In that unfinished script lies the quiet promise that the next flare, the next rotation of polarization, or the next slight drift in an orbit will open another small door. Beyond each door stands another hallway, not darker but deeper, where gravity, heat, and magnetism shape light into clues that wait for patient eyes to read.